Alright, so I already went through the whole beginning of this, so, and it just, for some reason, the recording fucked up, so I'm gonna try to just kind of do a brief overview of it, because you don't really need all of it to answer the question. I'll still explain what's going on. So you have a petri dish, you have a neuron right here, and you have your control liquid, which is basically what would normally be around the neuron in terms of potassium and Na concentration. You have your high potassium concentration, usually potassium is the lower one on the outside, and then you have your low sodium one. Alright, and then this is the probe right here. This is what measures where this is what measures the voltage. So I'm going to hit the control here and put that in there and find out what the voltage is. Alright, so right now we're on the outside of the cell, record data, that's 0. Going to go to 2. We're gonna record data. We have a negative 70 voltage in there right now. Alright, and this is saying what's the polarity of the resting membrane potential? It's negative, as you can see. That's a question. Alright, we're gonna go number 3. Alright, so this is on the outside again, and it's gonna probably be 0. So on the outside there's no voltage. Number 4. This is along the axon, record data, negative 70 voltage. What does it mean that the voltage just inside the membrane is negative? This means there are more negative charges than positive charges just inside the membrane. Alright. The membrane of most cells, including neurons, contains passive open potassium leak channels. Given the normal potassium concentration, which is low, and the resultant concentration gradient, which direction would potassium be expected to move, diffuse, through these leak channels? It would go out of the cell, since it's low concentration outside and high inside. Alright. Predict what will happen to the resting membrane potential if the extracellular potassium concentration is increased. It will become less negative. There will be less ions moving in general, because you'll have high concentration outside and inside the cell. Alright, and so now we're going to change this to high potassium and see if I was right. So now we have high potassium inside and outside the cell. So right now we're on the axon, we're going to record data. So axon intercellular here it was negative 70. Now it's negative 40. I'm going to go to position 3 and record data. Axon extracellular. So this one was 0. It is still 0. What a shock. Alright, this one's cell body extracellular. It's right outside the cell body, and this one's 0, just like it was before. And now we're doing the cell body. And this inside the cell body is moved to from negative 70 to negative 40, just like the axon. Alright, and now we're gonna go back to control here for a second. We're just gonna watch this right here and see what happens. Just gonna go. And the voltage goes back down. What effect does increasing extracellular potassium? I'm just gonna check if I'm recording still. Yes, I am, thank God. Alright. What effects does increasing extracellular potassium have on the net diffusion of potassium out of the cell? This decreases the net diffusion, because if you have more potassium outside when you already have a lot of potassium inside, you're just gonna make less diffusion. Alright, now we're gonna put that low Na solution in and see what happens. Okay, so we're going to record data just inside. So now we've gone from, in our control group, which was 70, or negative 70, now we've gone to negative 72 in the cell body. Which way would Na move across the cell membrane if there was open Na channels? So generally there's low inside here, and so it would go into the cell because there's high Na in. All right. We're going to go to position 1, which is just outside. It's going to be 0 again. I don't even know why they do this on both of them. 0 again, because it's not touching the membrane. And then this is along the axon. This is going to be -72. The membrane has open potassium channels, and changing extracellular potassium concentration results in a change in the membrane potential. Changing the extracellular sodium concentration does not significantly change the membrane potential. What do the results suggest about the number or state open or closed of sodium channels in the resting membrane neurons? There's going to be less. There is going to be mostly closed channels, because if they were mostly open, it would the change in sodium would have affected it more. All right, we're going to submit our results. A negative membrane potential was recorded when the tip of the microelectrode was D, both inside the cell and inside the axon. All right. I just realized that if I'm typing, it's going to kill my recording software, so I'm going to go into settings really quick. We go to hotkeys, and I'm actually going to clear all these so that it does not kill my recording when I type. Okay, we should be good now. Negative membrane potential. Okay, so yeah, both inside the cell and inside the axon had the negative. So which of the following caused a change in the membrane potential from -70 to -40 in the cell? An increase in extracellular potassium. Yeah. Which of the following has the most negative voltage between the inside of the axon and the outside of the axon with control? It's that one. Okay. And then here we go. So explain why increasing extracellular potassium reduces net diffusion out of the neuron. Okay, so there's already a high concentration of potassium in the cell, so if you increase the potassium outside the cell, the K will no longer want to diffuse outside the cell, since they are closer to equilibrium. I'm getting text messages. Okay, one sec. I have to just quickly send the Quizlet here. I am sorry. This is one second here. All right, sorry about that. So if you increase, so there's already a high concentration of potassium in the cell, so if you increase the potassium outside the cell, the potassium will no longer want to diffuse outside the cell since they are closer to equilibrium. Explain why increasing. Okay, I am probably just going to skip all this and just do this. So how does the extracellular concentration of sodium affect the resting membrane potential of the neuron? So when sodium concentration is increased, potential becomes slightly more negative. becomes slightly more negative, but only slightly, because most of the channels are closed channels. Alright, let's go to activity 2 now. How do we get there? Let's find out. Alright, so let's go to exercise 2 now. We're just going to go straight to the experiment. I don't want to... Okay. So, note that the time scale on the, okay, I'm going to try to pronounce this, oscilloscope has been changed from 1 second per division to 10 milliseconds per division, so that you can observe the responses recording sensory receptors more clearly. Okay. Click the first sensory receptor, so this one, to record its resting membrane potential. Alright. Note that the voltage inside the sensory receptor, and click record data to display. So it has -70 inside. The adequate stimulus for pancreas is pressure to vibration on the skin. Which of the following which will induce the largest amplitude receptor potential? I really don't even know what it's asking here. So, high intensity heat, moderate intensity pressure, moderate intensity chemical. I really don't know. So we're just gonna take a shot in the dark. We're gonna go with we're gonna go with chemical. Okay. You'll now observe how the sensory receptor responds to different sensory stimuli. Okay, click the pressure modality. Click on low intensity, and then click stimulate. Alright, so it stimulated a little bit, or the membrane potential went a little less negative. Alright. Now click. Okay, well, we can't record that. Now click moderate intensity and then click stimulate. So that one did it a lot more. Click high intensity and then click stimulate. That one did it even more. Okay. So we're going to record that data. Okay, now we're going to click chemical. We're going to click low and stimulate. Okay, chemical didn't even do anything. So I think I was wrong. Sorry, people from the group keep texting me. Yes, quit messaging me. Okay. Moderate. Yeah, it's not even responding to chemical. We were very wrong. Or I was very wrong. I'm sorry. So we're going to record that data. Now we're going to do heat. We're going to do, come on, hurry up line. Low. Nothing. So pressure actually affected it the most. This would probably make a lot more sense if I knew what this thing was. But, you know, that's okay. I think it's just showing that what these, so this is like a nerve ending, and it's trying to show, or not necessarily a nerve ending, but it's like a type of receptor, and it's showing which receptors act to what. So this one obviously is meant to sense pressure. Because when the thing poked it, it reacted. It didn't react to any of the other ones. It only reacts to pressure. Alright. So, why didn't the pancreas respond to high light? Intensity light. Intensity was not high enough. Light transducing proteins are not present. Wrong kind of light was... The light transducing proteins are not present in the something. I'm not going to try to pronounce it. I'm just going to embarrass myself. Alright. So now we're going to click this one. Okay. So that's what we're doing. We're trying to find out which things sense what. What does graded potential mean? That's the question we're supposed to get from this? I don't even know. Alright, note the voltage inside the sensory receptor and click record. So right now it's at -70. So receptors are chemical. Chemicals typically alternate. Which of the following modalities will induce the largest? Okay, so it told us it's going to be chemical. It probably told us on the last one too, and I just missed it. So pressure. Oh my god, we got to do all this again. Yeah, pressure didn't do anything. Moderate. Come on, come on. Oh, it's going to make us go through all this. Okay, record. Chemical. Yep, just like it said it would. Weird. Record data. Gotta do heat now. This is not terribly exciting. Yep, heat didn't do anything. What a shocker. Now light. Moderate. High. Wow, that didn't do anything either. Okay. Record data. Judging from these results, does light have a smell? No. What kind of question was that? Okay. Free nerve ending. So, click the... Okay. Note the voltage inside the sensory and record data. Okay. Now, it didn't even ask us, so we're just gonna do... Alright, so it does not respond to pressure, at least low pressure. Okay, I don't think it responds to any pressure. Oh, it did respond to high pressure. Interesting. Alright, so we're going to record that data. Chemical. Okay, didn't respond to low chemical. Okay, so this didn't respond to any chemical. Okay, and it does respond to heat. So this one responds to high pressure, and it does respond a lot to heat. I bet it responds to light too. Let's see. Oh, record data. I keep forgetting to do that light. So it didn't do anything for low light. Didn't do anything for high light. Or moderate light. Okay, so it only responds to heat and pressure then. All right. Why did the free nerve ending respond to several different modalities? It lacks membrane proteins in the sensory end. There are too few inhibitor proteins in the sensory end. Sensory end of the nerve is less specialized. I'm going to do the less specialized, yeah. Okay, submit. Okay, I still don't know what the answer to this question is. What does graded potential mean? I didn't see it in the lab. This is the membrane potential. Like I don't even know where in the lab that was. So let's go through these questions. See what we want. A very intense stimulus can sometimes stimulate sensory neurons that have evolved for a different modality or modality. Thus, with a blow to the eye, one sees stars. In this example, the photoreceptors in the eye are responding to intense pressure. Olfactory receptors neurons respond to low concentration of chemical odorants because their membrane proteins in the receptors ending of this sensory neuron that... Okay, which one are the... Olfactory. Wait, sorry. Next one. Receptors membrane proteins in the receptor ending of the sensory neurons that... I'm going with the second one, I guess? I don't know. The sequence of events starting with the sensory stimulus and ending with a change in membrane potential is called... So the sequence of events starting with sensory stimulus and ending with a change in membrane potential is called... Oh god, I have no idea. Sensory modality? I have no idea. Okay, well, let's look at the overview and see if we can find what it says. Grade potential. Man, it doesn't say anything. Here, I'm going to ask the group chat really quick and see what they got for it. Alright, so for now we're just going to skip activity 2 question because I really don't know what it is. Let's go to activity 3. Okay, there are a few different questions. Let's read the questions before this time to make sure we're really looking for them. If a neuron achieves action potential, how does the distance of the electrode affect the force of the action potential? Does distance of the electrode from the stimulus decrease the force of the stimulus? Okay. I assume it's gonna, like, the distance of the electrode is gonna decrease the action potential. What does the term threshold voltage mean? And what part of the neuron was investigated in this activity? Alright, we're just gonna go straight to the experiment. So, note that the stimulus duration is set to 0.5 milliseconds. Set the voltage on the stimulator to 10 millivolts. Okay. By clicking the plus button beside it. Note that the voltage produces a current that can stimulate the neuron, causing a depolarization of the neuron that is a few millivolts change in the membrane potential. Click single stimulus to deliver a brief pulse. Okay. Note, record the data. You will increase the stimulus voltage until you observe action potential at the recording of the electrode. Alright, so we're going to hit plus, stimulate. Oh, there it goes. Alright. Why is the action potential recorded by the second recording? Alright, let's see here. So S, I'm assuming S is the electrode, and this is the first, and this is the second. Yes, this is R2. Oh, so it's showing the delay. Okay, I see. Because it's getting sent down, and then this is like the amount of time. So it's like hits here, which is right there, and then when it gets here, it's showing right there. So delayed relatively to the action potential. So it's because the stimulus strength was too small. The axon used in the experiment is abnormally long. The action potential had to propagate from R1 to R2. The recording wires. I think I'm gonna go with this one. Yeah. So it was right. It had to go down. It hit R1 and then R2 first. How will the action potential at R1 or R2 change as you continue to increase the stimulus voltage? The duration of the action potential will decrease. The peak value of the action potential will increase. The action potential will not change. The peak value of the action potential. I'm going to go with B. You will now continue to observe the effects increasing stimulus voltage. Increase the voltage by 10 millivolts by clicking the plus and then single. Repeat this step until you stimulate the axon at 50 volts. Okay. So I'm going to go to 30. Stimulate. Alright. So let's see if it... Okay, record data. Oh, I was wrong. It doesn't change in peak. What changes then? Does anything change? It looks like nothing changes. An increase in extracellular potassium would depolarize a neuron. This depolarization would occur if neurons were damaged. From what you have just learned about the generation and action potential, what effects would this have on nearby axons? The nearby axonal membranes will, so that is smaller than normal, be depolarized to values near or above threshold voltages, have action potentials that are faster than normal, be no further depolarized to values. Okay, let's read it one more time. An increase in extracellular potassium would depolarize a neuron. Okay, so it'd have less of a charge. This depolarization would occur if neurons were damaged. From what you've just learned about generating an action potential, what effect would this have on nearby axons? The nearby axonal membranes will, that are smaller than normal, depolarized. Okay, my first guess is smaller. Be depolarized to values near or above threshold voltages. I don't think that's it. Have action potentials that are faster than normal. That's definitely not true. Be further depolarized to value. Okay, I'm going to go with the first one. Incorrect. So there's B. Be depolarized to values near or above threshold voltages. Okay. Okay, part of the problem is I don't know what threshold voltage means, which is actually one of the questions, which is slightly ironic. So let's look that up. Threshold voltage. Well, okay, I have to go to Google first because I have a weird extension. So threshold voltage. The threshold voltage, commonly abbreviated and blah blah blah, is the minimum gate to source voltage differential that is needed to create conducting path between the source and drain material. So okay, I see. So it is the minimum voltage required to create a conducting the source and the end. So in other words, it's the minimum voltage required for the signal to get to point A to point B. So that's pretty simple. Let's shorten this. All right. So let's whoops, that's not what I wanted. All right, let's see what we got for the first question. If a neuron achieves action potential, how does the distance of the electrode R1 and R2 in PhysioEx affect the force of action potential? Does distance electrode? It does not decrease the force. The force is not decreased with the force of the action potential is not decreased with distance the same goes for does the distance of the electrode from the stimulus decrease goes for the force of the stimulus, which is the same thing, right? I mean, what's the difference? Wait. Okay, one second. I'm just gonna check something. I'm gonna check action potential versus force. Force of action potential. Okay, this isn't gonna help us. Anyways, I'm just gonna put that as my answer. What part of the neuron is investigated in this activity? It's the axon, isn't it? Yeah, that's the axon. It is investigating the axon. All right. So now let's go to number 4. How do I? Just gonna go straight to the experiment. Does the frequency of action potentials increase when the stimulus increase intensity? So does the frequency of action potentials increase when the stimulus intensity increases? Okay. So let's do the lab now. Note that the stimulus duration is set to 0.5 milliseconds. No one cares. Set the voltage to 30 millivolts, super threshold voltage, by clicking the plus button beside the voltage display. You will use super threshold voltage in this experiment to make sure there is an action potential, as thresholds can vary between axons. Click signal thing. Okay, so let's do this. Deliver a pulse. We see the delay. Enter the peak values of the response in R1 and R2 in the field below, and then click submit data. Or it's 100. Click timescale on the simulator to change the timescale. Okay, timescale. With a lower timescale, the appearance of the action potentials will generate R1 and R2 will appear to be compressed in time but have the same peak values. That's my answer. Yeah, it's that one. You'll now deliver successive stimuli separated by 2-second intervals to observe what the control action potentials look like in this time scale. So we're going to go to 2. Okay. Note the peak values of response of R1 and R2. Click record. If you apply TTX between recording electrodes. Okay, what was the question? How do you define voltage gated sodium channels? Oh, whoops, I was looking at the wrong thing. Okay, how would you define voltage gated sodium channel? Okay, well, we'll figure that out. If you apply TTX between recording electrodes R1 and R2, what effect will the TTX have on the action potential of R1 and R2? What is TTX? I don't even know. So let's go find out what TTX is really quick here. The overview doesn't even say. All right, let's. I'm gonna click this one. Okay, so let's drag the dropper bottle axon between electrodes. All right. There was. Oh, interesting. It stopped it over time. Okay, we're gonna do new axon. If you apply iodine, I really have no idea what either of these are going to do. Drag the dropper. Okay, so this one had the same thing, it just took longer. This experiment was performed on Okay. So for simplicity, this experiment was performed on a single axon where the axon potential is an all or none event. If you had treated a bundle of axons, each with a slightly different threshold and sensitivity to the drugs, you would likely see the peak values of combined or compound action potentials decrease more gradually as more zones are blocked. Okay, so they're like painkillers, I guess. Why do you think TTX is not used during dental procedures? I'm gonna say irreversibly blocks, maybe because maybe it has lasting effects. Okay, it does. Okay. How would you define a voltage-gated sodium channel? This is a sodium channel that can only be opened through voltage stimulus. That's my guess. To be honest, I'm really not sure if that's correct or not. So let's look it up. Voltage gated. Let's just look up voltage gated channels. Are a class of transmembrane protein that form ion channels. They are activated by changes in electrical membrane potential. So I'm going to say activated because that sounds more scientific-y. Through voltage, through changes in electric. All right, so that's a good answer. So she looks like she doesn't want us to do number 5, so we're just going to skip to number 6. The experiment. Just the frequency. Well, let's go to number 2 again. Because let's look this up. Graded potential. Graded potential are changes in membrane potential that vary in size or opposed to being all or none. They arise from summation of the individual actions of Lin-gated or ion channel proteins and decrease over time and space. They do not typically involve voltage-gated sodium potassium. What does a graded potential mean? This means okay, let's actually like copy and paste this into Google, because this also does. Okay, it just gave me the same damn answer. So I'm gonna try to bullshit my way through this. This means the membrane potential. Changes in membrane potential vary in size instead of being all or none. I think that's right. I'm like 30% certain. Okay, let's go back. Let's do number 6 now. So experiment. Does the frequency of action potential increase with the stimulus intensity increases? Okay, that's pretty simple. Does the frequency of action potentials increase when the stimulus intensity increases? Okay, set the voltage to 20 and do single stimulus. All right. I don't think it's going to, because we already hit maximum. Like, we already hit almost 100. Like, just looking how they scaled this. Because if we hit 100, but they had left room for, like, higher, then it might, but I don't know. Increase the stimulation duration to 500 milliseconds. Okay, wait. At the site of stimulation, the stimulus keeps the membrane of the axon in the threshold for a long time, but this depolarization does not spread to the recording electrode. After one action potential has been generated, the axon has fully recovered from its absolute and relative. 1 second. Someone scream my name. What do you want? Sorry. After one action potential has been generated, the action is fully recovered from its absolute and relative. Oh god, this is boring. Okay. Measure the time between action potentials. This interval should be a bit longer than the relative refractory period. Click measure. Okay, measure. Okay, so measure the time between action. Okay, I'm gonna look up action potential really quick. Is that the peak that we're looking at? It is the peak. Okay, so I just wanted to make sure we were looking at the right part of it. So let's go. So there's the peak, 102, 202, 302. Okay, there's 100 milliseconds in each one. The difference between action potentials is sometimes called the inner spike intervals. Okay, from ISI, you can calculate the action potential frequency. The frequency is the reciprocal of the interval and is usually expressed in hertz, which is events per second. From ISI, you entered calculate the frequency of action potentials with prolonged 500 millisecond threshold stimulus activity. Convert ISI to seconds before calculating frequency. What? Okay. Fucking Christ. Okay. The interval between action potential is sometimes called the interspike interval. Okay. Action potentials are sometimes referred to as spikes because of their rapid time course. From the interspike interval, you can calculate action potential frequency. The frequency is the reciprocal of the interval and is usually expressed in hertz per second. Okay. From the ISI you entered, calculate the frequency of action potentials with a prolonged threshold stimulus intensity. So frequency equals 1 over ISI. Okay, convert to ISI before calculating frequency. It's 1 over 100, right? A stimulus intensity of 30 millivolts was able to generate a second action potential towards the end of the relative refractory period in activity 5. Okay, what's the relative refractory period? That's this. Okay, it's just the period afterwards. So, with a stronger stimulus, the second action potential can occur after a shorter time. Increase the stimulus to 30 millivolts by clicking the plus button. Okay. Yep, it increased the duration. Enter the interval between action potentials. So at 101 or 102, 162. So it's 60 between each one. So 1 over 60. I think I'm doing that right. I could totally be doing this whole thing, this part wrong, so it's really confusing to me. Stimulus intensity is 45. We actually already have the answer to this question. It's getting really late at night, so I'm just going to try to... Does the frequency of action potential increase when stimulus intensity increases? Yes. As you increase voltage frequency. So we already got the answer to that, so I'm going to move on to number 7 because I'm I'm getting tired. It's already like, this says 9:35, but it hasn't changed. I haven't changed the time, so it's actually more like 10:35. Here, number 7. I still have the fucking pre-assignment to do. So, experiment. What characteristics of a nerve affect conduction velocity for an action potential? I'm gonna assume it's the myelination, since that's what we're changing here, but we'll still do the experiment. So, click a fiber. Okay, click click fiber. Click the A fiber. Okay, I thought it said click one and only give you one choice. Note the stimulus duration is set to 0.5. No one cares. Set the voltage to 30 millivolts. Single stimulus. All right, so we got the delay. Record data. Note the difference in time between the action potential. Convert the time from milliseconds to seconds. Enter the time. I don't feel like doing this in my head right now. 2 msec to sec. 0.002. Calculate the conduction velocity in meters per second by dividing the distance between them. So 0.1 divided by 0.002. How will the conduction velocity in B fiber compare to A? Oh, I don't know. Let's do slower. So let's try. Let's see. All right, let's set the time scale on the kaleidoscope to 10. Okay. Single stimulus. Record data. Where is it? Where's record data? Oh, there it is. Whoops. So it actually was longer. It took longer. It's gonna be 0.01. So it's gonna be 0.1 divided by 0.01. Yeah, okay. Yeah, so that one definitely had a really long distance between them. It's gonna be 1. Alright, so what characteristics of a nerve affect velocity? Diameter and amount. Well, I just want to get back to the questions here, just so I can get the wording. Yeah, so smaller diameter and less myelination cause the conduction velocity Just be slower. Number 8. Let's make sure this recording's still going. Okay, thank God. I probably have to shoot myself if it didn't stop at this point. I'm getting really tired. Number 8. Let's see. Why is this so far? This is bugging me. What did you observe happening to a neurotransmitter release when magnesium was added to the extracellular solution? Okay, what did you observe happening in the neurotransmitter release when magnesium was added to extracellular? Okay, so we're going to be looking at this one mostly, which is at the end, of course. So we're just going to zoom through this one. We're going to do this. All right. Click low intensity. Stimulate. Okay. ACH is being released, but only a little bit. Okay, now we're going to click high and stimulate. Okay, now a lot more ACH is being released. Interesting. What does the stimulus intensity affect the amount of... Why does it... the stimulus intensity directly affects the amount of calcium entering the axon terminal. Yeah, I mean, the stimulus proportionally affects them. I'm gonna go with both A and B. Yay! So yeah, what's it called? The stimulus. Oh God, the stimulus directly correlates with how much ACH is released, or neurotransmitter, or whatever they want to call it, and how much calcium is entering the axon terminal. So you've just observed that each action potential in a burst can trigger additional neurotransmitters release. If calcium ions are removed from the extracellular solution, what will happen to neurotransmitter released at the axon terminal? There will be no change in neurotransmitter release. There will be more. I'm going to go with that one. Click no CA and see what happens. Okay, let's get a move on. Okay, alright, so. Oh wow, it didn't even release at all. Okay. Which experiment are we on? Number 8? So yeah, what I just want to read the question again to make sure. What did you observe happening to a neurotransmitter release when magnesium was added to the extracellular? Okay. So high. So yeah, I guess no calcium means... Why is there no neurotransmitter release from the axon terminal when there's no calcium ions in the extracellular solution? Action potential propagation in the axon is calcium dependent. Yeah, I guess that's true. Neurotransmitter channels in the nerve terminal are calcium dependent. Exocytosis. We're going to go with that one. Yeah, so exocytosis of synaptic vessels is calcium dependent. Predict question 2. What will happen to neurotransmitter release when low amounts of calcium are added back to the... So there will be... So we're going to go with that one. It'll increase a little bit. So we're going to click it. Okay. Alright, so that's exactly what we expected. Alright, the magnesium ion is another divalent ion. It can compete with calcium and block its role in neurotransmitter release. Click Mg extracellular solution. Okay. Note the solution also contains the same amount of Ca2. Okay. What will happen to neurotransmitter release when magnesium is added? I'm going to go with less. than in the control. Yep. Why did high-intensity stimulation fail to trigger the same amount of neurotransmitter release in the presence of extracellular magnesium as in the control extracellular? Magnesium blocks the calcium channels in the axon terminals. I'm going to go with that one, but let's read the other ones too. Magnesium blocks action potential propaganate. I'm just going to stop. Magnesium blocks the voltage-gated sodium channels in the axon. I'm going to go with the first one still. Yeah, okay. Submit question. All right. So what did you observe happening to neurotransmitter release? We observed magnesium blocking calcium channels near the axon terminal, resulting in less ACH release into synaptic cleft. And last, and certainly not least, activity number 9. Let's go to experiment. Okay, that's the question. Why were the peak values in the action potential of R2 and R4 the same when you applied a strong stimulus? Okay, let's find out. Observe the 2 neurons in the petri dish. What do you think the resting membrane potential at the receiving end of the sensory neuron and the receiving end of the interneuron? What do you think the resting membrane potential at the... I'm going to go with negative 70. Yeah, okay. Note the membrane potential at the sensory receptor of the receiving end of the interneuron and click record data. Right. If you apply a very weak subthreshold stimulus to the sensory receptor, if it's subthreshold, I don't think anything will happen. No response. I'm going to go no response. Let's go. Hey, look at that. Why is there no response at R3 when you apply a very weak stimulus? The peak value of the action potential at R2 is too small. Well, it didn't get past R1. Like R1 sensed it. The very weak stimulus does not depolarize the axon. I'm going to go with that one. Yeah. So the very weak stimulus does not depolarize the axon. I'm starting to understand this. This is starting to make more sense, which is good. Okay. If you apply a moderate stimulus to the sensory receptor, a larger depolarization will occur at R1 and the action potential will be generated at R2 and maybe R4. Okay, that sounds good to me right now. A small depolarization response will occur at R1 or R2 and the action potentials will occur. Okay, I still think this is more correct. Action potentials will be generated at all 4 locations. Small depolarization. I'm going to go with number 1. So yeah, moderate. So it happens at R1 and R2. Ah, it does happen at R3. Interesting. God, it's so R1 has like the exact same as the stimulus. This jumps up and down, like this is so strange. Okay. Record data. Why is there a larger depolarization response? It's probably because it got past the threshold. Why is there a larger depolarization response at R1 when you apply a moderate intense stimulation? The moderate stimulus closes more voltage-gated potassium channels at R1. Stimulus reduces the passive leak of R1. The stimulus reduces graded receptor potential of R1. R1 is the relative refractor period. Go with A? No. It's C. The stimulus induces a graded receptor potential. I have no idea what that means. Right. Apply a strong stimulus. Okay, this is what we need to know. So this, okay, so the question we actually need to answer: why are the peak values of the action potential at R2 and R4 the same when you apply a strong stimulus? If you apply a strong stimulus to the sensory receptor, a large depolarization response will occur at R1 and R3, and action potentials will occur at R2 and R4. Okay. Okay. Sorry, it just clicked to me that, okay, action potentials only occur here, and then depolarization occurs at the cell body. Okay. That probably should have clicked a lot sooner for me, but that's why the graphs look so different. Because, okay, and then this is starting to make sense. B, a small depolarization response will occur at R1 and action potentials will occur. That's not true because R2, because action potential isn't going to happen at R3. And action potential will be generated at all 4 locations. It's going to be A. Ooh, look at them go. Record data. Submit. All right. Let's go back for a sec. Why were the peak values of the action potentials R4 the same when you applied a strong stimulus? Why were they the same? I really don't know the answer to this. I'm gonna say because it was above threshold, and if your body lost action potential peak value over distance, it would not be able to send and receive messages as well. Alright, so that is the end of this. I hope you enjoyed as much as I did, because I didn't enjoy this at all. This was very boring. Anyways, I hope this helped.